Well, good morning. Well, at least it's morning where I reside. Considering the viewership that we have for some of these presentations, it may be afternoon, and if that's the case, good afternoon to you. It's a beautiful April day and sun shining. Temperatures are rising compared to where they've been the last couple of days. I hope that you find yourself in a comfortable seat, in a comfortable position, a comfortable chair, and are ready to tackle an issue that can be very confusing for a lot of folks. I know it certainly was confusing for me when I started my career outside of academia. I really didn't deal too much with salt index when I was an academic. You know, I would read about it and see some things occasionally. Run to some of my other academic brethren and what they had learned on the issue, and sort of just regurgitated what they were providing. But then when I started this job and started really working on the fertilizer production side of agriculture, I really had to dig into this topic a little bit more. So what you're going to get today is my attempt to maybe demystify some of the calculations that are employed. Hopefully, inform you enough so that if you happen to be on the manufacturing side of our industry and you're considering introducing a new product to the market, maybe give you some idea as to how you can calculate salt index for whatever raw materials you're using to construct your material. Um, and then also as an agronomist, how do I take what are provided as guidelines and employ that to make sure that I'm providing a good recommendation to my farmer and not putting him at risk for salt injury of the crop that he's planning to grow. I will admit the latter part of that discussion is a lot more challenging. If we're talking about this in a lab setting where I know all of the assumptions, I know what the salt index is of the various raw materials that I'm using to make my blended material. That's pretty straightforward. The math is a little painful. Again, I'm hoping that I can present this in such a way that you can replicate what I've done. Um, but it's even more confusing when you go to the field. There's so many other variables that you have to be concerned with. We'll walk through some of those. I will expose you to a tool that exists today. Um, uh, Part of the challenge with some of the tools that exist as well, how broadly geographically does it apply? That's certainly a concern, but it's just really difficult to provide someone a safe rate of a particular starter material that they can apply with their planter if it's going in the row with the seed, and minimizing the risk of injury to that seed as it germinates. So that's what we're going to cover today. As always, I like to provide you with a little bit of a framework of what we're going to be talking about. So some introductory concepts. This is going to be very introductory, just to sort of get us on a level playing field for understanding what salts are. We're going to talk about solubility. I've got a table. It's not an exhaustive table. One of the challenges of presenting in a PowerPoint environment are the confines of the size and making sure that it's legible by everyone attending the session. So this is not an exhaustive list. I actually found one, and maybe I could provide you the link if you're looking for it. I actually found a pretty good list of solubilities of different salts at different temperatures. And I was able to dump it into an Excel spreadsheet format. So if you're interested in that, just contact me, send a note in the chat. Obviously, just address it to me. Don't address it to the group specifically if you're sharing your email, unless you want everyone else to recognize who was there. That's the great thing about Zoom and most of these virtual meeting environments is you have the ability to just specifically address me. So if you're interested in getting that, I would be willing to share it with you. It's a pretty good list. It's a pretty good list of most of the things that we use in the agricultural field. So I'm going to talk, it's going to be very brief. I think there's only 3 slides just to get us on the understanding of what a salt is, understand about solubility. We're not going to talk ad nauseum about solubility. What we really want to get to is how does that impact osmotic potential, excuse me, or osmotic pressure in a soil environment. So again, we're not going to spend a whole lot of time there, just going to give you high level, get us on to the next step in the process, and that's fertilizer salt index. How is it measured? How do we use it to compare materials? This isn't something that I read too much about in a lot of academic publications, but I think it's an important thing to consider is there is a way based upon the salt index of a published material and a desired application rate to compare various materials and what the actual salt index would be at the as applied rate. So I want to share with you some of that math. I'm going to talk about how you can calculate a salt index of a blended material. So if I'm going to make the example I provide is 624.6, I'm going to show you just a couple of different scenarios, changing what I'm using as the raw materials to make that blend and how it actually affects what the salt index is of the final product. Again, if you understand the framework and you understand hopefully what I've assembled as an easy way, I'm basically going off of what Rader had published back in the 40s, and then it was repeated in the 50s, and then Mortvet updated it in the 90s and the early 2000s. But I'm hoping that it's presented in such a way that you can easily replicate what I've done. And then we're going to conclude the conversation with determining safe rates. And again, I say safe. I have quite a bit of experience with supplying starters, mainly as an experimenter, right? As a university professor evaluating different products, looking at the influence of rate on what ultimately happens with germination, and recognizing that what is a safe rate for one environment may not necessarily be a safe rate for another. So what I'm really going to be talking about is what are the major considerations that you have to make when you're determining what a safe rate is? What are some guidelines to sort of put you at least within the rails of what we think is safe? The challenge is if you start pushing it too much and you get way too close to the guardrail, occasionally you're going to hit it. And like I say this a lot, and I say it jokingly, but it's real. The easiest way to decrease yield potential is dramatically decrease stand. Every time it works, or every time it's applied, it usually works pretty effectively. So the last thing we ever want to do is dramatically decrease stand. We can obviously tolerate some level of stand loss, but a significant stand loss is going to create a yield limiting factor that you're not necessarily, or rarely, going to be able to overcome with some other mitigating physiological effect that the plant can produce, right? And different crops have different mechanisms for dealing with decreased stand. We're not going to dive into that. That's not the nature of this conversation, but just try to give you an idea of what you need to consider. Then again, I will expose you to the tool that exists presently that at least makes an attempt to quantify how much of X material can I supply to this crop, given some understanding of what the row spacing is. So if I'm talking 30-inch, 20-inch rows, am I talking even narrower? I think in the example they give, I think they really limit what your row spacing is. And then what is the opening space or the opening width on my opener for where my seed is actually going into the ground. All of these things have to be considered when you're determining safe rate. So it's a pretty cool tool just to evaluate, even if it's not terribly accurate. It will give you an idea of what would be considered a relatively safe rate. And then I want to walk through how do I evaluate the tool that they have with what we've talked about today in this presentation. So some introductory, and I see I've already got a cue. Yes, perfect. Yep. I've already got someone sending me. So if you want that list, just let me know in the Q&A and try just to address it to me. I'm not sure if that went to everybody or just to me, but it doesn't matter. Okay. Some introductory concepts. So we all, most of the time when I interact with folks and I say the word salt, you instantly think of the young lady carrying an umbrella, wearing the yellow overcoat. That's not that's sodium chloride. That's a very specific salt. Okay, so a salt is technically any chemical that's formed from the reaction of an acid with a base, with all or part of the hydrogen of the acid replaced. You can still have some hydrogens that cling on there. Phosphate is the best illustration of that. But that acid is connected to a metal or some other cation. Okay, so just to give you an idea of what an acid and a base are, typically when you're talking about bases, it's going to be some metal, right? So we have sodium hydroxide. You can have sodium oxide. You could have calcium oxide. You could have calcium hydroxide. It's usually going to have a hydroxyl or an oxide group on it. And then you're going to combine that with something that's got a hydrogen tied to the front end of it. So that could be hydrochloric acid, sulfuric acid, phosphoric acid, right? So all the things that you probably have forgotten from your introductory chemistry class when you were either an undergraduate or when you were in high school. But those two are going to form together. We're going to take the sodium from one, the chloride from the sodium from the base, the chloride from the acid, and we're going to ultimately form sodium chloride. Water is going to be a byproduct. Now, don't just always assume that these are going to react. This is actually a fairly strong exothermic reaction, meaning it's going to produce a lot of heat because that's a fairly strong base and that's a fairly strong acid. But there are other salts that we can create. I can take copper oxide, which is my base. I can combine that with sulfuric oxide, and I can make a pretty successful pesticide in the form of copper sulfate. So again, all I'm taking is a base and an acid and creating a salt. Most salts, well, all salts to some degree or another are soluble. Just to give you an idea how the nature of the salt affects its solubility, this really starts to matter when you're talking about blending materials. Okay, how much of ammonium nitrate can I put into solution and not be worried about creating a saturated solution that's got the potential to precipitate out ammonium nitrate, or if there happens to be something else in that water, if it's not dissolved or if it's not deionized water, if it's got some calcium in it, am I worried about some calcium nitrate precipitating out, right? It gets really complicated when you start talking about solute chemistry in an aqueous environment and making sure that I'm not precipitating out issues. That's not the nature of this conversation today, by the way. Just something that I wanted to point out. But typically the general rule of thumb is if I have a cation and an anion that have a lower valence state or a smaller number associated at the top of the charge, so this implies a +1, this implies a -1, this is obviously a -2, and forgive me for not using the correct form on these things. So this is a 2+, a 2+, a 2-. The lower the valence state, so if I have a 1 and a 1, pretty good solubility. So ammonium sulfate is a very soluble salt. A lot of ammonium sulfate or a lot of ammonium nitrate will dissolve in water. Now, it is a function of temperature. Again, if you want that Excel spreadsheet, it's got different temperatures. It doesn't have them for all of them, but for a number of them, it does. So if you're talking 0, it's obviously going to have a lower solubility. If it's a warmer temperature, it's obviously going to have a higher solubility. But in general, the lower valence states, the higher the solubility. It's not always universally true. But if you're talking about something like calcium carbonate, right, and I hope everyone recognizes pretty quickly that that's lime, is fairly insoluble. And that makes total sense. If you have any experience applying lime to a field, you pile it up at the end of the field before it gets applied. And even if you get a rainfall event, it's not going to dissolve. You can't do that with ammonium nitrate. If you decided to pile up all your ammonium nitrate at the end of the field, not that we use a lot of ammonium nitrate in agriculture in North America anymore, but just as an illustration, if I put that product at the end of the field, piled it up before I make my application, if I get a rainfall event, where's all the ammonium nitrate going to be? It's going to be right there where you applied it, and you're no longer going to see a pile. It's going to pretty much turn into water. It's going to go into solution. It's going to move into that soil profile. Gypsum is another product you probably have some level of familiarity with. Calcium sulfate. It's orders of magnitude more soluble than calcium carbonate, than lime, but it's still relatively insoluble. Okay, and again, that's a 2+ and a 2-, fairly insoluble product. Again, I just show this just to give an idea of what salts look like. And when we think about solubility, there's obviously limits to what you can put in solution. So let's now move from just talking about salts in general to putting into solution. And here's the major point of this whole conversation. The more ions of solute or of solute that I have in solution, so the more, go back a slide, the more ammoniums I have, the more nitrates I have, the more chlorides, the more sulfates, the more of those things I have floating around in solution, the higher the osmotic pressure. Okay, so now I'm introducing terms that may not be terribly familiar to you. So I actually stole this from a plumbing website. And this is why we care about osmotic pressure, osmotic potential, and the influence that it has on water movement within a soil profile, and more specifically with regard to the placement of a fertilizer material relatively close to the seed, is how much does that affect the seed's ability to imbibe or take up water to begin the germination process. So this is an illustration of osmosis. If you've ever wondered what a reverse osmosis system is, this is exactly what it is. So we have this semi-permeable membrane. This is just for illustration purposes. If let's say that these are both pure water at this point, the levels between the two are going to be identical. As soon as I start dumping solute or a salt into this side of this little P-trap, it looks like a P-trap to me, then the water is actually going to move from this side of the channel to the other to try to create equilibrium between the two. Remember, um, natural systems prefer to reside in equilibrium. So if there's a lot of salt over here, water is going to move away from this channel in order to maintain the equilibrium. This is exactly what happens with the germinating seed that has fertilizer material that ultimately dissolves, right? It's got to dissolve if it's a dry product. If it's supplied as a liquid, it's already in solution. That the salt, the osmotic pressure that results as a result of the application of the fertilizer material, it's going to pull water away from that seed. And if this gets too strong, you can decrease germination of that seed. And if you have had any experience with getting a little bit aggressive with starter fertilizers and experience this, you're likely to never make that mistake again. Again, I've seen it. I've seen it with farmers' fields. They get a little bit of aggressive and hey, I got away with it last year, and then this year I couldn't get away with it. So the question becomes, can we quantify this effect and have a basis of comparison for different fertilizer materials? And that's what they discovered in the late 30s, early 40s, and said, okay, let's start determining a salt index. So the initial method for estimating salt index was applied, or they were measuring osmotic pressure from soil. We don't do that anymore experimentally. So if we're producing a new fertilizer material, we submit it to a lab to determine what the salt index of that product is. It's not occurring in a soil environment. It's actually occurring in an aqueous environment. And we're not measuring osmotic pressure. We actually measure electrical conductivity. Now, the good thing is there is a relationship between electrical conductivity and osmotic pressure. Okay, but at least initially in the 40s, they were measuring osmotic pressure in a soil environment to quantify what the salt index was of various fertilizer products. And as you can probably imagine, the list of materials that they were using in the 40s doesn't necessarily look anything like the fertilizer materials that we have at our disposal today. And I'll show you what that list looked like from that initial publication in the 40s. As we progressed into the later 40s, there was a more rapid assessment technique that was developed. It was actually published, I believe, in 48, and that is that electrical conductivity approach. It really wasn't really fully accepted as chemically as an analytical method for soils and fertilizers until the late 50s. It was published in the Soil Chemical Methods book in 1958, but it sort of displaced this osmotic pressure approach. Excuse me for that. Now, the one thing you have to realize about salt index is it is a relative measure. All of the fertilizer materials that we report salt index for, they're all relative to the standard that was established in the 40s, which is sodium nitrate, which actually makes the math a little bit easier, to be honest with you, when you're comparing various fertilizer materials or when you're making an attempt to calculate what the salt index is for a blended product. So this is a good thing. And don't be surprised that this is relative to sodium nitrate. Everything that we do is relative to something else. There always has to be a point of reference for almost anything that we do experimentally. So this is what the actual salt index calculation looks like. I'm not going to show you what all the osmotic pressures. I mean, I could. If you really want that publication, it was published in Soil Science in 1943. You can go find that article. I do have a copy of it. Osmotic pressure of the material divided by the osmotic pressure of the sodium nitrate multiplied by 100. Now, this is an important point about this because this matters when you're comparing different materials. Is recognize that the salt index that is calculated for all of the products that exist, they're all applied at an equal rate, at least going back to Rader's work in the 40s, an equal rate of 100 pounds per acre. We actually try to emulate that in an aqueous environment today. So if you submit it to the lab, what I would envision happen, and I've actually never run a salt index. I've run labs, but I never really worked on fertilizer materials. It was more plant analysis and soil analysis and water analysis. It wasn't necessarily fertilizer analysis. I would assume that you're supplying a fixed amount, and I know they're supplying a fixed amount of whatever that new. So if I'm developing a new product, they're going to put 2 grams. I'm just going to use 2 grams. I'm going to put 2 grams of that material, 2 grams of ammonium or sodium nitrate. I'm going to bring that up to a specific volume. Okay. And then I'm going to stir it, and then I'm going to measure electrical conductivity. There might be some filtration process. There might be some other intermediate steps, but that's the basic concept. So just recognize that everything goes back to this 100 pounds per acre basis. This will become important later on when I'm talking about how do I compare different fertilizer materials and what the salt index is, specifically at an application rate of this specific material. Okay, just hold on to that, because remember, this salt index number that is reported is a function of all materials being applied at the same rate, which you should probably immediately recognize that not all fertilizer materials would be applied at the same rate. If I'm trying to hit, like, and I use this in a couple of slides, if my desired nitrogen application rate, let's say in a pop-up fertilizer application, is 8 pounds, and that's typically the limit that most guidelines put as far as what is the maximum amount of salt material you can supply with the germinating seed. The old rule of thumb is 8 pounds if I have a certain amount of CEC. Well, if you're comparing two different fertilizer materials, the rates of application of different materials will be different to hit that same 8-pound rate. But the salt index, as it is reported, assumes that everything's applied at an equal rate. Okay, but there's an easy way mathematically to make that accommodation, and I will expose you to that here in a few slides. So this was the actual, and I don't know how to get rid of this stinking, go away. Hey, I guess that's how you do that. So this is the salt index of common fertilizer materials. So we have, this is from the Rader publication in 1943. So this, if you're looking at these, they don't necessarily match what you see with, say, Mortvet's updated list in 2001, published in Fluid Journal. It doesn't necessarily, most of what I see coming out of the academic community and even testing labs is going to match more closely what Mortvet published in 2001. There's a reason for that, and I will share that here a little bit later. But what they did was okay, so ammonia, we're going to put it at that 100 pound per acre rate. This is the salt index. Again, this is all relative to sodium nitrate. That's why sodium nitrate is 100. So obviously ammonia is a less saltier material than sodium nitrate at equivalent rates. And then we can, what we ultimately want to do, if you want to compare materials, is, okay, so what equivalent basis do I put this on so that I can compare ammonia to ammonium nitrate? Because ammonia has 82% nitrogen, ammonium nitrate only has 34%. So I have to put on essentially 2 times as much ammonium nitrate to supply the same amount of nitrogen as I can with, let's say I'm targeting, if I'm putting on 100 pounds of ammonia, I'm putting on 48 pounds. Well, if I'm using ammonium nitrate to put on that same 47 pounds, I have to put on 2x, over 2x the rate to get there. So how do I put this on an equivalent basis so that I can compare these different materials? Hence this term called the partial salt index. So essentially what we're doing is we're dividing the salt index by the concentration of nutrient in the material to come up with this 0.57. I won't walk you through the math. If you wanted to emulate it, if you really wanted to see all of that, I can show it to you. I've sent Excel spreadsheets on this to folks who are trying to understand salt index. So I have a partial salt index for all of these different fertilizer materials. This is actually what we use to compare materials. This is actually what we use when we're putting together blended products and we're trying to get an estimate of what the salt index would be of a new material that we're manufacturing. Okay, so again, these are all relative numbers relative to sodium nitrate. This is ultimately the number that you're probably going to be seeing the most of. Now, one more thing about this particular slide is this is per unit of nitrogen. There's a number, there's not a number, there's obviously limits to the number of ways that you can do this, but this is only on a nitrogen basis. So all I'm taking into account, so even for this map, you'll notice here in a subsequent slide, if I put this partial salt index on a unit of phosphate, this number doesn't match because MAP has a lot more phosphorus in it than it does nitrogen. So this number is going to be lower. Okay, and then we can actually account for NP and K and come up with what the partial salt index per unit of nutrient, not just nitrogen, phosphate, or potassium. What I'm going to tell you is it doesn't matter which approach you use as long as you're consistent. This isn't typically the way that people think about it, but for me, I occasionally want to think about it this way. But for your use, this probably isn't the approach you're going to take, but I just wanted to expose you to all we're trying to make sure we're doing is we're accounting for what this number right here looks like once I take into consideration nutrient concentration. Okay, this may not make sense. Hopefully it will as we proceed through here. These were the phosphate carriers they had listed. Notice what I said before, the salt index of the partial salt index of MAP, if I'm just considering phosphate, is dramatically lower than what it looks like for nitrogen. So if I go back to the previous slide, MAP was 2.45 if I'm just considering on a unit of nitrogen basis, and it's 0.49 if I'm looking at on a unit of phosphate basis. Here's the other challenge of using what Rader had did in the 40s to where we are today. He was using reagent grade of these materials. It doesn't really affect the nitrogen products all that much. You might see some level of variability, but there's a huge difference between fertilizer grade MAP and reagent grade MAP. Much higher nutrient content in reagent grade MAP than there is in fertilizer MAP. So it gets a little bit wonky if I'm using these values to calculate what my salt index is if I'm blending materials. That may not be clear, but just if you want more of that, let's connect offline and have that conversation. Okay, so again, these were the predominant forms of phosphate in their day: super, single super, triple super. And then we have potassium carriers as well. I don't know why MAP. That should have been, this was obviously a slide that I didn't get updated. I'll try to update this if you want to copy this. Obviously this was an oversight on my part. So, or maybe I just transposed it when I copied this particular slide. So then I have multi-nutrient materials. So again, this is the way to compare. It's not just nitrogen, phosphorus, or potassium basis. This is on all the nutrients contained within that fertilizer material. So this is the sum of MAP of the nitrogen and the phosphate in the MAP, taking that salt index, dividing it by the sum of those materials, and coming up with this 0.405. Same thing for DAP, ammonium polyphosphate. And what you'll notice is these numbers are fairly similar to what we see for fertilizer grades. Actually, I differ with the math on this one. I'm not sure who's right at this point. But just to give you an idea, again, this may not make total sense, but hopefully as I go through here, this will start to become a little bit more clear. So what were the issues with Rader's approaches or the values that he was reporting? There isn't anything wrong with it. But they did use reagent grade materials, not a commercial fertilizer grade, and that can be problematic for phosphorus materials. Most of the potassium, most of the nitrogen products, it really doesn't have that big of an influence. And even for these, even though there are some pretty big differences in the concentration of nutrients contained within those products, the actual effect on the salt index calculation is relatively small. So take that for what it's worth. This could make using that information a little bit challenging. So what did Mortvet do? Okay, he came back and said, okay, let's just update this with today's commercial forms of fertilizers. And you'll notice pretty quickly, I'm just going to use MAP as an example. The salt index of a fertilizer grade MAP is not considerably, but it is lower than what it is for reagent grade. So 26.7 for fertilizer, 29.9 for the reagent. You're going to see the same effect on the DAP as well. So essentially, he just updated this list to be more reflective of the fertilizer forms that we are using today compared to what they look like in the 40s. Again, none of these actually ammonium nitrate changed slightly, but most of the impact on these were fairly small, but you did see a little bit of an impact on MAP. And again, this is on a per unit of nutrient. Notice I say use this one. So if you're wanting to calculate the salt index of a new blend, or you want to compare salt indices of different fertilizer products, use this list. And this is not an exhaustive list. There are other published lists that exists, but use this one. Don't use Rader's. They're fundamentally the same thing, but Mortvet is using more commonly used fertilizers for this list than Rader was back in the 40s. Here's where I do disagree with Mortvet's math. He reports a 0.405. By my math, it should be about 0.24. It's not a huge impact, but I'm anal enough in the math that I do. Is it just rounding error? I'm not sure. Or is it just a transposing error when they published it initially? I'm not sure. I'm confident that my math is right. So use whichever one you think is the most appropriate. It's not going to make that big of a difference at the end of the day when you're comparing fertilizer materials or you're calculating a blend. Updated list. It's got DAP, APP. Notice some of the things that fell away. I know that there's still triple super out there. I know that there's still single super out there. That wasn't reported in the list that Mortvet published. I did add one that wasn't published on his initial list, and that was potassium hydroxide. Technically, this is not a salt. This is a base. But it is a way to put some potassium into solution, and it does have a lower partial salt index than most of our other forms of potassium salts, potassium sulfate being the one exception to that general rule. So, okay, great, Robert. That's very, very helpful. You've spent 30 minutes describing what was done in the past. How do I use this tool for me today? Okay, let's take an example. Now, this is just an illustration. Don't run away from this and say, Robert says DAP is better than APP. That's not the take-home point, okay? DAP has other risks associated with its use as a starter material that I'm ignoring. I'm just using this simply for illustration, okay? I just want you to get comfortable with the math and how to do these comparisons. So let's assume that my desire is to apply 8 pounds of nitrogen in the seed furrow. Okay, so I can apply either ammonium polyphosphate or I can apply DAP. Which is my best choice? I have to say this again. I'm ignoring other factors. Now, obviously, I'm comparing a liquid and a dry. Depending upon the configuration of your planter, one of these is not going to be a reality. It's going to be one or the other. Okay, for the sake of argument, I'm ignoring all of that. I'm also ignoring the fact it's really influenced by soil pH, but if I do have a soil pH that's near neutral, or if I have a poorly buffered soil that doesn't have the capability to buffer against changes in pH, if I'm using DAP as my source, this is a basic salt. So whenever this is supplied to the soil, it will increase pH, at least in the zone where this application occurs. And if the pH gets too high, I can actually produce free ammonia, and that has its own issues associated with risk of injury to a germinating seed. I'm ignoring all of that, okay? For your purposes as an agronomist, if you're comparing different materials, you can't ignore that. I'm just doing it for the sake of this illustration because the math is easy. So I have DAP, it has a higher salt index. So if I look at the salt index, if I apply these at an equivalent rate, DAP is going to have a higher salt index than APP or ammonium polyphosphate. So your conclusion would be APP would be my better choice, right? Well, hold on just a minute. They both have a similar partial salt index per nutrient applied. Now, this is a full accounting of the nitrogen and the phosphorus. I will tell you if I'm just accounting for the phosphorus or if I'm just accounting for the nitrogen. I think for all of the illustrations that I provide, actually there is one where I show you both ways, just to show you it doesn't matter. You get the same answer, but you just have to make sure the approach that you're using, okay? But for almost everything that I do, I'm assuming I'm accounting for the nitrogen and the phosphorus, and I'm accounting for the nitrogen and the phosphorus in this material as well. So they almost have identical partial salt index numbers. But if you do the math, it requires a lower rate of DAP to hit this 8 pounds of nitrogen per acre rate than it does for the ammonium polyphosphate. So DAP from a salt index perspective alone, again, ignoring the other issues that are associated with use of this product, would be the better choice. Okay, so let me show you how you walk through that comparison. So this is assuming that I know, or I'm using all of the nutrients contained in it. So notice this one is just on a per nitrogen basis. Notice I get the exact same solution at the end. It doesn't matter as long as you're consistent. Okay, so I have 1846.0, okay? In order to hit that 8 pound per acre rate, I have to put on 44 pounds per acre of this material. Strangely enough, if I supply that, the nitrogen application rate will be 8 pounds. I'm not worried about the phosphate at this point in this particular example. Although if you're comparing these two at that 8 pound rate, I'm going to get a little bit more phosphorus if I supply that APP. We're not worried about the phosphate in this example. I'm just pointing that out. The total nutrient is the sum of 8 plus 20. It has to be taken into account because I'm doing the total nutrient approach. So essentially what you do is that 0.456, which came from this table. So DAP has a partial salt index of 0.456. APP has a partial salt index of 0.455. That's where those numbers come from. I multiply 28, which came from the sum of these two by the partial salt index, and I actually get the salt index for this material at the rate of application. Okay. Again, remember, this number was derived from an equal application rate of these two materials. If I want to adjust it based on my desired application rate for them individually, I have to do some new math. So this one has a lower salt index at the rate of application. I hope that's clear. And again, I don't see this used too frequently for these kinds of comparisons, but I find this highly valuable if I'm really wanting to dig into what the salt index is of different products applied at different rates. You have to do this math to do that. This illustration, all of the math is the same. You notice everything is the same. The only difference is instead of the total nutrient, which was 28 and 35, now it's just 8 and 8 because I'm only accounting for the nitrogen. I have to do new math to come up with this partial salt index. Notice these numbers are dramatically different. This is very easy to calculate, but the solution at the end of the day, you're getting the same answer. Again, all this is trying to do is put an equivalence between different fertilizer materials. Because if I compare just the salt index as reported in this first column, it assumes that all of these materials are applied at the same rate, and they're almost never going to be supplied at the same rate to achieve the same nutrient application rate. And I hope that's clear. Again, I don't see this used too frequently this way, using this approach, but this is a pretty easy way to compare different materials. Again, there's other things to take into consideration, but this is a simple approach to compare the salt index at a desired nutrient application rate of different fertilizer products. Okay, so let's take this a step further. And the only other thing I would say here, it's already illustrated up here, but just to echo it again, is the nutrient content of the fertilizer matters. It's not just the salt index. This is why partial salt index is so important. Okay, so let's do a little bit of math. Hopefully this is straightforward. You can find these published. I'm taking a completely different approach because I don't like to repeat what others have done. If you want to see what others have done, you can go look at their math. I like to show you new math just so you can see it done with different products. So, and I've never manufactured this product. Part of it was, I do know the way some people manufacture it. So I don't want to give away trade secrets. Not that it's a trade secret necessarily. 624-6 is a pretty common starter fertilizer material. I don't know of anybody that actually makes it the way that I'm proposing. Again, it's just for illustration. So if I'm using ammonium polyphosphate and I'm using potassium chloride, and this is monopotassium phosphate, that's the MKP from a previous slide. This is the nutrient content of these various fertilizer materials. If I'm going to put these all into a liquid blend, okay, how much of the respective products do I need? And then what is the resulting salt index of this new formulation, this 624-6 product? This is how you go about this math. Okay, so 1034.0, I'm going to need 1,200 pounds. This is sort of trial and error. You set this up in an Excel environment, and you just keep tinkering with these numbers till you get this to be the right concentration of the blend that you desire. There's probably an automated way with some really sophisticated math. I'm pretty cool with math. I'm not that cool, and I haven't spent that much time. Maybe the math isn't all that impressive, but I just haven't sat down and tried to come up with an automated way to do this. It's much easier for me to do it with this approach. So if I put 1,200 pounds of 1034.0 into a 1 ton product, what is the nutrient concentration? And this is where this concept of per unit comes from. I'm not a fan of that terminology because it gets really, really confusing. I will show you where the 20 number comes from. It's a mathematical constant, but for some reason we've glommed onto it. So that 1,200 pounds, you do the math, that's going to be in the final analysis in this 1 ton, that's going to be 6% nitrogen. That's going to be 20% phosphate contributed from ammonium polyphosphate to the final product. I show you this math here in a subsequent slide. It's pretty straightforward. Again, this isn't highly complicated mathematics. I feel like I'm always talking about math in this particular webinar series, though. Do the same thing for KCl. I'm going to put on 62% product. I'm going to put 113 pounds in that blend, that 1 ton product. That's going to contribute 3.5% K2O to the final blend. I'm going to use this MKP, 52% phosphate, 35% potassium. I'm going to supply it at a rate of 140 pounds per ton. Do some simple math. I calculate what the percentage contribution from this material is. You sum these up and voila, you get this 624-6 product. Then all I'm doing is I'm going to sum the total nutrient from, obviously there's some rounding error here that's missing. The total nutrient from this is 27.2. The KCl is 3.5. The MKP is 3.6 plus 2.5. That's the 6.1. I know what the partial salt index is per unit of nutrient. I ran out of space, so I didn't include that long descriptor there. These, you pull these straight from those previous tables. So just to prove it to you, this 0.097 comes from right there. There's the monopotassium phosphate, the 0.097. That's where these come from. I'm pulling straight from there. I do my math. I multiply 27.2 by 0.55. I get 12.4. You sum these up. And for this material, the 624 product, 624-6 product, with these raw materials as the starting products, this is the resulting salt index. Okay. Just to show you this one more time, the math is the same. All I changed was I supplemented KOH, or potassium hydroxide, for potassium chloride. Potassium chloride or potassium hydroxide has a lower partial salt index. So what do you suspect happens to the final salt index of this material manufactured with this product? It's even lower. So if you apply the equivalent rates of these two 624-6 products, which if you're supplying on a nutrient basis would be the result, which of these two would be a safer product to supply? This one would be the one that's got the KOH in it, okay? This is how you make these comparisons. If it's the same product and you're just looking at from a manufacturing process, what's going to give me the lower risk? This is very simple to do. KOH is going to be my product of choice. The problem is this is going to have higher costs associated with it. This is not an economics presentation or a financial presentation. This is purely the chemistry. Let's do another one. Same 624-6 product. I'm using AAP, but I'm using MKP for all of my potassium in this particular blend, but I'm going to have to spike it with some UAN, or you could use urea. Again, I'm not promoting that these are the right formulations. I'm just showing you these for illustration. So if I use 28, higher per unit partial salt index than any of the other products that I've used, but the amount of application is really, really low. So what's the net effect on the overall salt index of this product? This is an even lower salt index for this material. If I were to use urea, I could probably make this even lower. And in fact, if you look at the book value for most of the 624-6 materials that are available in our market space today, it's typically less than 12. It's typically around 11.5. Okay, so again, they're obviously using a different manufacturing procedure to get to that low salt index beyond using what I'm proposing here. Again, this is just for illustration purposes. So again, you can easily replicate this math if you so desired. So this is always a point of confusion, so I'm going to clear it up right now. Where does this unit, so you see it published, it says there's 20 pounds per unit. What the heck does that mean? Where did that 20 pound come from? Well, it's only valuable, it's only valid when you're calculating a 1 ton blend of materials. Okay, so maybe the easiest way for me to show you is this. So where does this 4.5 come from? All right, so if I supply 900 pounds of ammonium polyphosphate, it's got 10% nitrogen. That means I'm going to be supplying 90 pounds of nitrogen to this ton of material, and that's coming from the ammonium polyphosphate. Okay, so that 90 pounds represents what percentage of nitrogen in the final blend? Okay, so you get this 90 pounds of, this is, if you go back to the very first webinar we did in this series talking about fertilizer calculations, this looks fairly similar to dimensional analysis because it is. If I'm supplying 90 pounds of nitrogen from ammonium polyphosphate, what does that represent in the final blend? Well, if I do my dimensional analysis, I'm going to get rid of, let me actually do the pen. I got to get rid of my ton. I got to get rid of my ton. Interestingly enough, the pounds go away. So this is now on a percent basis. So I'm dividing 90 by 2,000, multiplying it by 100, and I get 4.5% in the final formulation. This is how you do this math. It's not complicated. Here's where the 20 comes from. If you divide 2,000 by 100, which is obviously the reciprocal of how it shows up here, mathematically it does the same thing. you get 20. So if you divide 90 by 20, you're going to get 4.5. So I guess for the ease of memorization, they just said 20 pounds is a unit. That confuses the heck out of me. That's not the way I think. Doesn't matter. You get to the same destination regardless of whether or not you remember this 20 or you use the dimensional analysis that Robert typically promotes. Okay, you're going to get to the same destination. Okay, this is where that 20 pounds per unit comes from. All right, so I've got 14 minutes to talk about safe rates. This is a very important statement, maybe the most important statement of this presentation. The SALT index, as it was developed initially, and even for the way it's utilized today, was not developed to allow for calculation of what a safe rate would be of a fertilizer application. Okay, there are too many other variables, and I'll show you some of those here in a subsequent slide or two. It was developed simply as a way to compare fertilizer materials and their risk of injury as the result of the resulting osmotic pressure that would occur as a result of the application. Okay, it's just a way for us to compare materials. And I would argue it really wasn't a great way to compare materials unless you're using it like this. Because I have read, and it's actually in Mort Vet's publication in 2001, it's a fairly common product, and I've heard this from a lot of folks, 721.7, you shouldn't use it because it has a salt index above 20. Well, if you apply it at a low enough rate, you can actually get the salt index below 20. Because the assumption for the salt index that was developed for that material was based upon an equivalent rate of all other materials. So you really have to account for what your desired application rate would be for that product to determine what is safe. So if you wanted to use that 20, then that may not be a bad guideline. I'm not sure that I'm ready to actively promote it at this point. But if you wanted to say, thou shalt never apply a fertilizer material that results in a salt index at the application rate, if it exceeds 20, that's probably a pretty risky application rate. And what you're going to see with the tool that I'm going to show you, that's essentially what they've done. Okay. And again, that may not make sense, but here in a moment, hopefully it will. I'm not going to go through these. This is the general rules of thumbs that we have. It's stated, you can find this in a lot of academic publications. I know I've said this myself several times. There's obviously going to be a safety factor built into this because you never want to expose people to risk. I know folks that exceed this 8 pounds. It always makes me nervous. They can get away with it if the conditions are right. If the crop is fairly sensitive to, or is not terribly sensitive to salt, that's the other thing that you have to take into consideration. This is obviously just for corn. This is a specific one for soybean for 2x2. Then you have other people that say, thou shalt not ever supply fertilizer material with soybean. I know of folks that do it. That's in the seed row. Again, it's all a function of making sure that the osmotic pressure is not so high that it affects germination. So if you really want to play with what some safe rate calculations are, Ron Gelderman had done some work in the mid-2000s. I remember when this was being published out of South Dakota State University. He worked on all the factors that ultimately influence the potential for salt damage. That's going to be the crop. Is it a sensitive crop or is it not? What's the soil type? Again, if you're talking about a finer textured soil, it's going to hold more moisture. You can get away with higher rates of application. If it's a very coarse textured soil, doesn't hold a lot of moisture, your rates of application are going to be lower because there's greater risk of not having adequate moisture to keep the salt, to dilute away from the salt. Your salt concentration can get too high. Soil moisture is a consideration. Row spacing, am I talking about 30-inch rows or 20-inch rows or 10-inch rows? Again, I don't know what flexibility he provides on the row spacing. I don't know if there's a limitation or not. What's your seed furrow opening width? Am I talking 2 to 3 inches? Because that matters, because the more soil I have this salt interacting with, the lower the influence on the osmotic pressure in close proximity to that germinating seed. So just to give you an illustration of what the tool looks like, it's actually a pretty simple interface. It is available right now from ipni.net. That is a good link. I confirmed it this morning. So you select your crop. The only real thing you change is your crop, the fertilizer material, what your seed furrow opening width is, what your row spacing is, and that what your tolerated seed loss or stand loss would be. So I'm fairly risk averse. I probably wouldn't go over 2. Maybe I would stretch it to 3. Again, the easiest way to decrease yield is to decrease stand. So I'm not going to be very tolerant of much in the way of stand loss. Using these assumptions, this is what they calculate as far as a safe rate of fertilizer, assuming it's a fine textured soil and assuming it's fairly moist conditions. Now, Robert is interested in, okay, what does this look like for the final salt index of the as applied material? And you can probably guess really quickly, if all of those were initially determined using a 100 pound per acre rate, and the salt index for ammonium polyphosphate was 20, I remember that, you probably don't, then it's going to be north of 20, but it's just going to be slightly north of 20. And it turns out that's correct. So using what he recommends from this model, this is again a way you can use the information that I'm providing with a tool that he's got. There's another step in this process to make another evaluation. 1034.0, 108 pounds per acre rate. I'm supplying 10.8 pounds of nitrogen per acre, 37 pounds of phosphate per acre. My total nutrient content is 47.5. My 0.455, which comes from that table from the MortVet publication. My salt index at the application rate is 21.6. That's a little north of the 20. It's actually going to be just north of 9 gallons per acre. A lot of folks that I know, again, this doesn't represent the entirety of the population. 5 GPA is typically what they'd shoot for if they're using ammonium polyphosphate. Don't take this as Robert is promoting that everybody should be using ammonium polyphosphate. That's not what I'm saying. This is just what I'm using as an example. People get really tied up in sometimes what I use as illustrations. If I talk about prices, that gets even scarier. People really get mad at me. Now, what if I changed one simple assumption in this model? So this first line is for a moist soil. What if it's borderline? So it's not dry, but it's not overly moist. It's in that sort of gray area where, you know what, if I don't get rain for a couple of days, it's going to get dry. But I've got a couple of days that I can hold out where there's still going to be adequate moisture in that soil. The recommendation drops down to 72 pounds per acre. What does that change the salt index to for this material at that application rate? Well, it drops it down to 14. That's going to be closer to a 6 GPA. That's more in line with what I typically see for folks that are using ammonium polyphosphate as a starter product, specifically in the seed furrow, is somewhere on the magnitude of 5 to 7 gallons per acre. This 9, I know of folks that use 10. I'm not saying it's not a safe rate, but it's a riskier rate than obviously a 6. So what the salt index allows us to compare is the relative risk of these various products. Okay, so you could do this same thing if you wanted to plug in 624.6, 721.7 at equivalent rates of some particular nutrient. You could do the math and figure out which one is going to be less risky. Okay, and that's really how the salt index was, what it was originally designed for. So just in conclusion, no confusing, and you're probably looking at this, and I hope this made some semblance of sense and sort of demystified how these calculations actually function. It is a reliable method of comparing different fertilizer materials and the relative risk that they present to a germinating seed. The challenge with the initial salt index as presented is it assumes that everything is applied at the same rate. And in the real world, that's not going to happen. So I would argue that you really need to go through that calculation that I showed where I can compare different materials to figure out what is the salt index of this material if I'm supplying it at a specific rate, okay? Because again, the concentration of the nutrients in the material does matter, and it matters for this reason. I didn't share this earlier. If I'm comparing MKP, monopotassium phosphate, to say potassium chloride, the total, because it's, well, actually that's not a very good one. Well, if I do it on a per nutrient basis, it's pretty good. So I'm going to do it on a per nutrient basis. Everything is relative. That's what's so confusing. So in potassium chloride, there's 62 units of nutrients. Okay. In monopotassium chloride or monopotassium phosphate, there are 35 plus 52. There's going to be 87 units. So I don't have to put as much salt in the solution to achieve the desired concentration of nutrient, if that makes sense. That's why higher concentration fertilizer materials generally have lower overall or lower salt indexes when you consider partial salt index. Okay. The salt index of a lot of the known raw materials that we use, very simple to calculate what the salt index of a newer formulation would be. Again, the ones that I went through, it's just for illustration, just to give you an idea of how to use that math. And then the challenge for those of us that call ourselves agronomists and ultimately want to use these materials to grow crops is it's not simple to just consider osmotic potential in the soil. So if I have some measure or some estimate of that, of what my osmotic potential is at the day of planting, considering what the influence on osmotic potential or osmotic pressure will be for the fertilizer that I'm supplying at the rate of application, it's not that simple. Okay, it's much more complicated than that. Ron's work out of South Dakota State is really the first attempt that exists that I've seen. There may be others that exist, I just haven't seen them, that tries to account for as many of those considerations when making a recommendation as to what a safe rate would be. Okay. We do have time for questions. I do see that there are some Q&A. I don't know. Okay, these are primarily just request. So I do have one from Dwayne. Shouldn't you calculate that? So I'm not for sure what particular slide that was on. Shouldn't you calculate that at the desired FOS application rate? That is why you would use those. Yeah, for Dwayne. Again, that was just for illustration. I could do that for phosphorus. So what Dwayne is asking about specifically is this guy. Yes, I could very easily do that for phosphorus. I just wanted to illustrate what it would look like for nitrogen. If you did it for phosphorus, these numbers would all be the same. Okay. Again, this is your opportunity to go through that math. If you follow the steps that I've outlined, you may come up with a dramatically different answer. Okay. Mine was just saying if I'm trying to supply 8 pounds of nitrogen, which admittedly is not a lot of nitrogen, this is what the SI for these materials would look like. If I had time, I would run to my Excel spreadsheet, Dwayne, and I would do that for you. I could show you how to do that comparison. It's very simple. These numbers would change. These would all be the same. This number would change. And obviously these numbers would change. You could very easily do that. I just use nitrogen for illustration. If you're really comparing MAP and APP, it's primarily going to be for phosphorus. I just wanted to do something a little bit different. And then I do have another individual interested in the spreadsheet. I hope you found this of value. Again, trying to demystify the salt index. Again, I know when I first was introduced to it, it's like none of this makes sense. It does make sense. The challenge is you really have to follow the math to make it make sense, because some of the terminology gets a little bit confusing. Again, being a math person, it's much easier for me to follow the math. And that really leads me back to, once I know the math is right, then I can figure out the terminology and how they're trying to define things. For those of you who stuck around, I'm just about to flash the QR code so that you can capture your CCA credits. For those of you who are listening to this recorded, obviously you're going to have to take the quiz to get those credits.